Okay, last one is about escape speed. So we got this planet, and it's got a let's see, it's got a radius of big R and a mass of capital M. And the first thing we want to find is the speed that an object on its surface needs to have if it's going to completely escape the planet's gravity. So that is what we call escape speed. So we're going to say this object has speed VE at the surface. So what does this mean? What it means is that the planet has, or the body has enough energy to completely get away from the planet's gravity. And so the way you approach this is you look at it in terms of an energy balance. So we say this is our initial condition here, number 1, and at condition 1, or state 1, it's got potential energy equal to negative capital G, and we're going to say this object has a mass of little m, which is going to fall out eventually. It's going to cancel, but for now, little g, big M, little m over the planet's radius. Not squared, sorry. You don't put the square in potential energy. Boy, I can't believe how many times I've made that mistake. So this is the potential energy at the start. At the start, it has kinetic energy equal to 1/2 mv squared. And what's the speed it has initially? It's this VE. So it has escape speed. And what happens is it launches, and maybe it curves a bit, whatever. But eventually it gets way far out. And so we're going to call that state 2 and show an arrow there saying it's way, way, way far out. That's why the arrow. So it's like, I don't even want to draw it. It's so far away. That's my point. Okay. So when it's way far away, it's going to have a potential energy of, well, it's going to be negative G, big M, little m over R. But we're talking about R going to infinity. So maybe I should write here that R goes to infinity as you go out to number 2. So if this becomes infinity, then bigger, it gets bigger and bigger and bigger and bigger and bigger, it becomes infinite, then this is going to become 0. So 0. And then the kinetic energy, when it gets way far out there, well, basically you just want to, you want to find sort of the minimum speed you can have here that'll get you all the way out here. So as you go out, you'll recall the potential energy is increasing asymptotically towards 0, remember? So if this is like your increasing distance from the planet, increasing R this way, then your increasing potential energy is like this, and you are approaching U equals 0, right? So we just want to be able to get all the way out there, which means we want enough total energy to get all the way out here as far as we want. Since U will never be greater than 0, as long as we have 0 total energy, then we can get there. So really what we want is E mech equals 0. And if you remember one thing from how to find escape speed, remember that E mech equals 0. Just set E mech equals 0. I'm going to circle this, I'm going to box this in red and do like little stars around it like I'm in 3rd grade or something. Because E mech equals 0, yes, I'm an 8-year-old girl. E mech equals 0, and that will get you escape speed. Okay, because what we're doing here, these are the components of E mech over here. So what we're doing here simply is we're saying total mechanical energy on this side equals total mechanical energy on this side, which is 0. So negative G, big M, little m, over big R, plus 1/2 mve squared equals 0. Let's get our, I don't know, let's use purple. Let's use purple to cancel the m's. And what we get then is that what comes out of all this is VE squared equals 2 big G, big M over R. This is big R. So we're using, to be clear, we're using the planet's surface there because I said in the question starting from the planet's surface. And so your escape speed, if you want it like this, is just the square root, obviously, 2G big M over big R. There you go. You're all set. And that is the answer to problem A. So, for part A. Part B. Let's look at part B. Part B says if you're launched straight upwards at a speed v, what is the maximum height you're going to reach? So I'm going to draw a new diagram down here for part B. Here's your planet, and here's the well, let's see. Let's draw the radius of the planet like that, big R, and you are launched from the start, and you get up to this far. And this distance here, the distance you get above the ground is h, and this is like your, you know, your little r axis. So as r increases, you're going out. Initially, you have some, actually it's straight up. Initially, you have some initial speed v, and then you reach the top and you're done. So again, we'll label our states. We're going to say this is state 1 and this is state 2. So in state 1, your potential energy, actually I'm just going to do some, we'll do it in purple, why not? Okay, potential energy is negative capital G, big M, little m. And so again, our you know, your object has a mass of little m, which is going to cancel out, so it'll all be cool. But it's negative G, big M, little m over R. And kinetic energy is 1/2 mv squared. That's your initial speed, whatever it is. And then for part 2, you are at a distance, big R plus h is your R. So now you've got potential energy negative G, big M, little m, over capital R plus h, because this is your total distance from the center of the planet. And you want to find how high you're going to go. You're launched straight upward, so you go straight up, you go, and then right at the top you sputter out, or you don't sputter out, but you reach a standstill and then start coming back down. So kinetic energy, kinetic energy equals 0 there. So when we do an energy balance here, a mechanical energy balance, what we get from the left side is, how about blue for this round, is negative G, big M, little m, over R, plus 1/2 mv squared equals negative G, big M, little m, over big R plus h. Okay, so, pardon the noises there. So what cancels? Let's see. Our m is going to cancel, so that's convenient, just like I told you they would. And then we can do, I don't know, we can do like, let's do like v squared equals, and then we can put a 2 times, we're going to have a G and a big M coming out of this, so 2gm times, and this is going to be a, so this comes over, I'm really kind of skipping steps, and I encourage you to sort of do this explicitly yourself. 1 over R minus 1 over R plus H, is that right? So I brought this over, and then factor out the G and M, this being a positive 1 over R, so it's still minus, okay, yeah, so I've got it. So this is where it gets kind of a little trickier, but we wanted to find H, right? So we want to solve this all for H. What's interesting, well, not so interesting yet, but we'll get to it. So let's find, let's see, what's a good way to do this? If we multiply this whole thing by R and then bring an R under here, trust me, I know what I'm doing. V squared equals 2g, no, actually I don't know what I'm doing, hang on. 2g big M over, wow, no, nothing, this is horrible. I guess we'd have to, let's see, 2g big M over big R times 1 minus big R over big R plus H, and this is just getting worse, but let's do, so let's bring this over here and do v squared over, oh, actually that's not too bad, over 2gm slash r. So that's taking this whole thing and popping it under the v squared equals 1 minus big R over big R plus h. So then big R over big R plus h equals 1 minus v squared over 2gm slash r. And you know what? I'm just going to go ahead and sort of skip ahead to part C here. What you'll notice is we calculate our escape speed up here, right? Escape speed squared is 2gm divided by r, which, if you can read my craptacular handwriting, is what we have here. It's this term, so just to sort of back up and make it clear what happened. This term here came and became this term here. So it's the same thing, it just got divided under, and that became this term here. But what it is, it's actually, this is equal to, this is 2gm over r, this is equal to VE squared. So what you can actually say, and this should make it somewhat nicer, is that big R over big R plus H equals 1 minus V squared over VE squared. And so then, blah, 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 let's see. Let's move this over there, and I'm going to multiply both sides by R plus H and divide by this. So I'm going to take this thing here, and I've used green and orange together, so you probably want to vomit at this point. But I'm going to take this thing and put it underneath the fraction, and this thing is going to come out up to here. So what's going to happen then is we're going to have R over 1 minus V squared over VE squared equals R plus H, because I just did that, flipped those, and wow, if you are still listening to this, I am very impressed. I think you're kind of, you know, you've got an appetite for punishment if you do, but hey, you know, that's your business. Yeah, so what do we do? I mean, I guess, so then we go with H equals, needless to say, if you actually had to do a problem with this stuff on the test, you would be there, okay? I mean you'd be able to plug in numbers or whatever. So don't feel like you really need to be able to follow the symbolic math all the way through. If you're feeling like you want to shut this video down and go, just sit in a corner and cry about the horrible things that Dr. Smith made you derive, and then go ahead and do that. You should only be here if you really enjoy pain. So let's see. This is going to be, we're going to be subtracting 1 over here, or subtracting r. So r times 1 minus 1 plus v squared over ve squared. Oh boy. Over 1 minus v squared over ve squared. And, whoops, sorry. And then, oh boy, let's switch to another color just to totally gross you out. And this will cancel. And so what you get then in the end is H equals big R times v squared over, VE squared over 1 minus v squared over VE squared. Or if you prefer, it might look a little neater to say H equals R times 1 over VE squared over V squared minus 1. That's dividing everything by V squared over VE squared. Or your final option is to say H equals R times V squared over VE squared minus V squared. And this is probably the most readable version. So if you're still with me, first of all, bravo, thank you. This is your answer to part C, and your answer to part B would just be to substitute in the 2gm/r for this. Okay, so wow, there's got to be an easier way to have found that, although I don't know what it is. Anyway, so what's neat about this, or neat, what's interesting about this is that this term here is dimensionless, and this gets into this idea that we have in many sciences, including physics, of a dimensionless parameter. So the idea is that if you find the ratio of someone's speed to the escape speed of the planet, then that is like, you can use that to find this number here, which is dimensionless, and this is like how many times the planet's radius they'll be able to rise. So it's just kind of interesting, because then you could divide the r through and have dimensionless stuff on either side. So you could have like h over r equals v squared over VE squared minus V squared. And scientists like this kind of thing where you can get it into dimensionless ratios, because then that sort of, that shows how you can apply this equation to any planet. So if you had the radius of Mars and its escape velocity, you could find out how high something you shot on Mars, how high up something you shot on Mars would go. And the idea then is that if you shot something up on Mars at, say, twice Mars's escape velocity, then the height it would reach would be some fraction times Mars's radius, and then the same ratios would apply on Earth if you shot something at twice Earth's escape velocity. Sorry, twice Earth's escape speed to the object's height and Earth's radius. More information than you ever wanted to know, certainly, but hey, I live to please. So, there you go, and that should be it for the whole symbolic review.